Don't you just love getting the spot before lunch? Okay, we'll do this quickly, and I'll try and keep you interested and get you out of here vaguely on time. So thank you very much for inviting me down here. Are we going? I'm clicking. There we go. British law is recorded on vellum. That means it's written. I don't know if it's literally written by scribes, but it's written on vellum, which is the skin of calves. And there was a bit of an uproar recently when it was decided that they would stop doing that, and they would, I don't know what they were going to do instead, put it on paper or digital, print it on hard disk or whatever it was. There was an outcry. The government found millions of pounds to guarantee that in the Victoria Tower, which is what you see on the left, there would continue to be law stored on vellum. That's worked pretty well from the 15th century onwards. We've managed to not lose too many of our laws, at least not accidentally, only by voting. Okay. This is the time I get to show my holiday photographs. That's me in Beijing at the Imperial Academy, looking at the Qianlong stone steles, which is a series of stones engraved with 13 classic tales from Chinese, I don't want to say mythology, the Chinese classic stories. They're engraved on stone. They've lasted since the 18th century. The picture on the right-hand side, you can see the surface is beginning to go. So we're losing some of that information now. I mean, obviously, we've made a note of what we can. Damascus steel, which was known, famous for holding a sharp edge and being one of the strongest forms of steel, was made in Damascus, or that part of the world, from the 3rd to the 18th centuries. And the recipe, the system for making it has been lost. There's people trying to recreate that. They can make steel that has the patterning you see on the right, but they haven't made anything which is believed to be the same stuff. So that's something we've lost over the years. It was really useful for many, many years. We wanted Damascus steel, lasted 1,500 years or so, but no one wrote that down in a way that survived and that we have available to us now. So there's some things, bits of information that we keep in a certain way. They're all in the past. They've all lasted quite well. They're not going to last forever, perhaps. So now it's pseudo audience participation. Quick thing, what's a bit of information, each of you, that you would store for a long time, that you would want to pass on to your descendants or just the world in general in 10 years or hundreds of years or maybe thousands of years of time? Have a quick think about what that is. And there's some suggestions. So everyone's thought of at least one thing by now. Who thought of something that was digital? Hands up. Who thought of digital stuff? Okay, not as many as I hoped. Was it really digital? Was it documentation? Was it a picture, which nowadays is all digital? Everything nowadays is digital. The graph on the left-hand side is just a quick, sorry, kind of quite small. It's on logarithmic scales, there's more and more digital stuff. Every 10 years or so, there's 10 times as many digital things out there in the world, whether that started off with one computer in each town, or one computer in each home, or one phone in every pocket, or coming soon, the Internet of Things, which will mean hundreds of devices. Everything is digital. All information is born digital now. Movies are made digitally, they're edited digitally, they're sent around the world digitally, they're displayed digitally. How do we store this information? Well, in the past, we stored information on stone tablets that last maybe a few thousand years at best. Or we stored it on paper that lasts tens, maybe, hundreds of years. We have experience of that. Photographs, color photographs don't last quite as well. And the more and more recent technologies last less and less long time. And that's what the graph on the right is kind of showing. To the right-hand side of the dotted line is when we got into digital technologies for storing things. And there's some examples there. There's optical discs like CDs or DVDs last a few years. Magnetic tapes last a handful of years, despite what the manufacturers tell you. If you go to a data archiving center, they'll tell you they replace them all every 5 years because they don't trust them. So as we've moved on into this future of more and more digital information, eventually almost all information seems to be digital, and we've had talks already today starting to demonstrate that. The systems we're using for storage are less and less permanent. So what are we going to do about this information we want to pass on for a long time? This is what we're doing at the moment. We're putting it in data centers. Here's a couple of data centers. The bottom right one is a Facebook data center in Sweden. That's a private system. The top left one is the NSA in Fort Meade. That's a so-called public system, though actually I suspect it's quite hard to get in there. Data centers are big and they take up a lot of space. The rate data is increasing in the world. They take up more and more space, and you can do a few quick calculations and show that within 150 years or so, the whole surface of planet Earth is going to be covered in data centers. That's probably not right, and but something's going to have to give. Something's got to change. The problem, well, another problem with data centers is all that hardware becomes obsolete. It doesn't last a very long time, and we change the systems we're using. So all the computer machinery inside those buildings has to be replaced every 5 or 10 years or so. While it is running, it's really expensive. They use a lot of power to spin all those disks. Then they use the same amount of power again to cool the whole thing down, so, unless you go to Sweden, where they've probably made a cost saving there. So it's not really a very efficient system, not on the big, long-term way of thinking of things. I usually have to gauge the age of my audience before I talk about the next slide, or the next couple of slides. But these are the kinds of things in this picture that are being used at the moment. They have a limited lifetime. You've seen all of those things around, I'm sure everyone in this room has. They will probably be replaced, just as these things have been replaced. I have used all of these technologies. I'm sure there's people in the room also who have, and there's some people in the room that have no idea what maybe any of those things are. There isn't time for me to discuss them all. They're all digital information storage technologies that have gone. If you've got any of those things in a box in your garage or in your loft, it will have decayed. The information won't be there anymore. If by some miracle that hasn't happened, you haven't got a reader for it, so there's nothing to do with it anyway. And if you have got a working reader for it, it doesn't plug into your computer, which is where you want information these days. If those don't work, ooh. Okay. What are we going to do instead? Well, another part of my working life, apart from what I'm talking about today, is studying genome and molecular evolution. This is a little representation, or one of many, of the evolutionary tree of all the life on Earth. It's not really got all the life, but it's got a lot of things in there. And of course, the thing that unifies all of these, that has passed on the information from one organism to its descendants over 3.5 billion years, is DNA. It's that molecule inside every cell of every living organism, which carries information, that has the instructions. It's called the hard disk drive of life sometimes, and copies are passed on from cells to the descendants, from one generation to the next. It's a really good information carrier. It's lasted a really, really long time. And I'll remind you a bit about what DNA is. We've heard it mentioned very times. It's a molecule. It forms a long chain. It's made of 4 subcomponents, discrete molecules, nuclear bases or nucleotides that come in 4 types that we conveniently labeled A, C, G, and T. And you can stick them together, or nature can stick them together in a chain molecule in any order. It's remarkably stable as a molecule. It forms the famous double helix structure, which you see here, which is in most of the ways of representing it. But actually, the information it carries is just in any one strand of the DNA. Once you've got the one, the second one, you've got no choice left, so to speak. There's only one way of making it so they will bind together. So the information, you can just think about one strand of DNA, which is a chain molecule with these different components in it. And the information is just there in the series of molecules, or the series of letters. So you can think of it as almost like a strip of paper with a series of letters, A, C, G, and T on, in any order. And there can be a code, and that can store information. In the human genome, or any living thing's genome, there's a genetic code. That's the way the cells store information. If it helps you to think about it, you can think about it like Lego, with 4 colored bricks that you can clip together in any order to make a kind of tower. And we could imagine the information is stored somehow in the sequence of the different colors along that chain. So I'm not the master of this technology. Lego's about 25 million times bigger in terms of just in a long line than DNA. DNA is really small. Also, it will then fold up, which you can't do with Lego. So it's not a perfect analogy, but it's a surprisingly good one. So we have a lot of technologies that are very good at manipulating DNA. Humans have learned how to do this now. So we can write DNA. Copying DNA is really easy, but making that first copy is actually quite difficult. This is a facility in California, which is one of the companies that leads the world in doing this, and they have a clean room, and it has what is essentially a very complex, very accurate inkjet printer, and they can use that to make little fragments of DNA according to a design that you or I give them by emailing them, essentially. So we can write DNA. We're not terribly good, but we can do it. We can certainly read DNA, and we heard a little bit this morning already about how that's done. A few years ago, this was a state-of-the-art machine, and it's a big thing sitting on a table, and you can't see the computer that's underneath the table that's driving the machine. And one of my colleagues standing with his back to the machine because it's not very interesting to watch it. These are the machines we use now. It's fairly routine for looking at the genomes of living organisms, for biological research, and increasingly in health-related research. My colleague and Ewan Burney and I were in a bar, this bar in Hamburg a few years ago, and we were having a meeting about the way our institute, the European Bioinformatics Institute, should store genome data. And we have a lot of hard disks, and we spend a lot of money every year on disks, and on a computing facility, on electricity, and we were being asked how we could be more efficient about that. And at the end of the day, we were thinking slightly more imaginatively about ways of doing that, and we realized that we have all the components we need to use DNA as a digital information storage medium. It's a molecule that is essentially digital. It's a sequence of letters, A, C, G, and T, just like the information on your computer or on your phone is a sequence of bits, 0 and 1. We have all the technologies for writing the message in DNA. We can transport it around the world. It's actually very easy to make copies of it, and we can read it back. So we've got all the components we need. We didn't plan our experiment in exactly this format by drawing little pictures, but it's surprisingly close. We did indeed sit in the bar with napkins and pens, working out whether we could do it. So here's our experimental design. Start on the top left with my laptop computer with information on it. Encode that information into the designs for some pieces of DNA. Ask the company in California to make that DNA, FedEx it to us back in England, do a bit of laboratory work. Actually, it went to Germany for genome sequencing, get the information back, read it back, see if we've invented a system that can store and copy and transport and recover information in DNA. Not biological information, not the instructions that make the cells of a living body work, any information that you could hold in a computer. So the genetic code won't do. The genetic code is very good for storing the instructions for making proteins that have functions in your body or in a living organism. It won't do for what we needed, and we had to invent our own code. Here's a little schematic that we drew up, but I won't explain all the details, but basically you start at the top with information on a computer, and through a various set of manipulations, you convert that to the designs for some pieces of DNA. So it will either look like this in my computer, or this if we think of it as DNA, or this if we think of it as pieces of Lego. And we asked the company in California to make those pieces of Lego, and they supply them to us. But unfortunately, it doesn't come neatly in an easy readable form. The writing process isn't that great, and we essentially get something analogous to a box of broken bits of Lego with some errors and some bits missing. And our fragments are definitely in there, but there will be a few mistakes, and the reading machine makes a few mistakes as well. But we knew this would happen, and we know about error-correcting codes. They're ubiquitous. They're inside your phone. They're inside your digital television signal. They're actually inside your hard disk drive, but they don't tell you about that because they don't want you to think that your disk drive is always making errors and correcting them. They want you to think it's perfect. But error-correcting codes are a well-known thing, and we could invent a code that would correct the errors, even though the pieces of DNA we got back wouldn't be exactly what we wanted. So we did that. We chose some things to encode in our first kind of proof of principle experiment. So we're shy retiring people, so we used a photograph of our institute, which has my and Ewan Burney's offices visible in it, though I haven't highlighted them because we wanted to get the message out there about what we do. And we were thinking about, what kind of information would you store a long time? And in the end, I'm going to tell you why DNA is a good system to use for storing information a long time, but we were thinking of socially valuable things like a soundtrack of Martin Luther King. We picked an MP3 that had a excerpt from his I Have a Dream speech, Watson and Crick's famous paper where they first described the structure of DNA, which was published in the journal Nature, where we hoped we'd get our research published, so we thought we'd suck up to them by using that. And we'd have liked to have done all of Shakespeare's works, but that was too big a file size, and so we picked just the entirety of Shakespeare's sonnets. So some files on my computer. We asked the company called Agilent in California to make the DNA. They sent it. It arrives in these tiny little test tubes. The picture in the middle at the top is me holding one up to the light to try and see if there's actually any DNA in there at all. Our files combine to a bit less than 1 megabyte of information. In terms of DNA, that was an invisible, virtually invisible dust in one test tube. We gave it to the guys in the laboratory with their sequencing machine. We said, this is DNA, sequence it just like you do with a genome. Give us the results. We got the results back from them as a computer file telling us what the DNA had been. We reversed the coding procedure. We decoded the information. And this one's hard to get across visually in a very exciting way because I show you 2 copies of a photograph and I say they were the same, but they were the same. And I show you 2 copies part of a PDF file and I say they were the same, but they really were the same. And I shouldn't take the time, but I love doing it. I was phoned up by a journalist from Switzerland who said, could you send me the resulting file for the photograph because I want to check it's the same. And I said, it was the same because they've got the same file size. And if you look at every single bit inside that file, it's the same. And she said, no, I want to look that they're the same. And what does it mean to send someone the file? So I emailed her the file, and she was happy that that was the same one. I don't know if I sent her the original or the resulting one because they are the same. And after it's been converted into an email message and sent to Switzerland and shown on her screen, is that the same one or not? Who knows? But she phoned me back and thanked me and then said, yeah, I was right, they were the same. It works. We kind of invented this new field of research. I didn't think this would stop me doing my genome evolution research, but it's taken over my life. Other people have started doing it as well, which is great to see. In the news this year, a team from Technicolor, the film production company, working with scientists at Harvard University, have encoded one of the world's first science fiction films, Le Voyage dans la Lune. Someone will tell me at lunch. And a team, Microsoft have got interested. They're working with the University of Washington. They made the big breakthrough of encoding pictures of cats, so they've won. And also pop videos and so on. And I can't resist telling you that the art world loves this kind of story as well. I've been working with an artist called Charlotte Jarvis and the Kreutzer Quartet on a project Charlotte calls Music of the Spheres, in which music is not played but is stored in DNA and added to bubble mix and blown in the air. It would work beautifully in here, Royal Institution, if anyone's listening. So I've just finished up. Why are we doing this? Well, why might we do this? Well, we did it because it was great fun, and we thought that would be the end of it, but actually people are really interested, and it's quite an interesting system. Before I can tell you why we should do it, I'll tell you why we're not doing it yet, and it's ridiculously expensive at the moment. We think we need to reduce the price by a factor of about 10,000 to 100,000 before we can sell this to people. That sounds scary, but in genomics, it's not a problem, right? Sequencing the human genome, which was finished 15 years ago, cost $3 billion. Today, you can do it for 1,000. That's a million-fold increase in improvement in 15 years, and that's just routine. We just expect to see that in genomics. 15 years. The big expense at the moment here is synthesizing DNA. It's creating the DNA. Maybe wait 10 years, it'll probably be 1 million times cheaper. At the moment, it's a little bit too expensive. People are working on it. This morning we saw, actually, there's physically in the room a nanopore sequencer that's the size of a Mars bar that fits in your hand. I only have a photograph of one, sadly. And the processes for creating DNA are getting more and more efficient, and the pictures at the top are systems that are taking over from this inkjet kind of procedure. So why should we do it? Why are we even interested in DNA for storing information and potentially doing so for a long time? Well, one is it's crazy small. I mean, it's just ridiculously small. So I told you that 1 megabyte is kind of invisible. Well, what does that mean? That means that if you filled that little test tube, which is like as big as 2 joints of your little finger, that would be 1 or 2 petabytes of information easily. And that's like 1 million CD-ROMs. I didn't have time to pace it out today, but 1 million CD-ROMs is like if this whole stage area was about this deep in CD-ROMs and I was wading around in it, right? That much information fits in something smaller than your little finger. So that's useful. That saves the surface of the planet from being covered in data centers. It means you can get all the information in the world, not in a crossed-out data center, but everything in the world at the moment. I've never been giving a presentation before where my support act, my opening act, explained what a zettabyte was. That was a fantastic moment for me. The whole world has, when we drew that graph, 3 zettabytes of information. Actually, now we're more like 10 or 20 zettabytes of information in the whole world. You can fit that in the back of 1 truck if you store it in DNA. You couldn't afford to do that. But that's how dense DNA is for storing information. So that's convenient. Come on. It lasts a really long time. And here my expertise as an evolutionary biologist helps, because I know we've done the experiment about how long DNA lasts. It lasts 20 or 40 or 60,000 years or even 700,000 years when they've studied ancient horses. And that's not a carefully prepared laboratory sample. Those are dead things that lay on the ground somewhere cold. It lasts a really long time, and the facilities you need to store it aren't that complicated. At most, you need something like the Svalbard Global Seed Bank, which is in the Arctic Circle and is naturally very cold. But we all own the facilities if you want to do it in your own home. So it's easy to store, and it's really easy to make copies. If you want to make copies of a book, you use a photocopier, and you do 1 copy at a time. And if you want 1 million copies, it takes a long time. If you want to make copies of things on a CD, you need on a a hard disk drive, you need a plant that makes hard disk drives, and they're complicated places like the bottom. If you want to make 1 million copies of DNA, you need a desktop machine on the right-hand side like that does PCR, and it takes maybe half an hour, and you go from a test tube with 1 copy to a test tube with 1 million copies. It's kind of self-assembly. It's genius. That's why DNA is used in natural cells, of course. And lastly, we're never going to lose the machines that do the reading, because we're never going to get bored of DNA. Because of the healthcare, because it's in every single one of us, because it's going to be the future of personalized medicine, we're always going to have DNA reading machines. It's never going to be obsolete. If I find a sample in 1,000 years or 10,000 years or 100,000 years with information written in DNA, I will have, or my descendants will have the machine to read it, because they're still going to be reading DNA. None of this Betamax or paper tape stuff that goes out of fashion and decays and we don't know what to do with it. It's always going to be there. We're still working on this. It's not quite viable yet. If anyone wants to invest in our company, we're trying to set up, come and see me later. Aside from that, thank you very much.